Alright, we're going to give this audio a shot, but I worry that it might be too windy out here. Here is a student submission for number 5. Prove that any simple abelian group is isomorphic to ZP for some prime number P. So in other words, any simple abelian group has to be cyclic and of prime order. So this student started off with let G be a simple abelian group and let little g be a certain element. So little g, the elements generated by little g, is a normal subgroup. Now, why does it have to be normal? Because we're in abelian, so everybody's normal in abelian. Now, it has to equal the whole g, the whole group g, because g is simple, right? It's definitely a subgroup of g, and since capital G is simple, then the only option is that it's the entire thing. It couldn't be anything smaller, because then that would be a normal subgroup and G wouldn't be simple. So it has to be that that element generates the entire group. So capital G is cyclic with that little g as its generator. Okay. So then they start wondering about the order of that single element, or equivalently the order of capital G, since we now know that it's a cyclic group generated by that single element. So if it is infinite, then some people from here said if it's infinite, then it's just like Z, and so it has infinitely many subgroups, and so it's not simple, and that's totally correct. This person specifically said if it's infinite, then consider the subgroup generated by G squared. Well, that would be only, half the elements that were generated by G, and so that's an even, that's a proper subgroup of the whole thing. So then G wouldn't be simple. So boom. So really that's the same problem, just looked at a different way, or maybe more specifically. Whatever. Anyway, so now they're like, okay, so since we know that it's finite cyclic, is it prime? Well, let's call P the order because we know it's going to end up being prime. But let's just say maybe it's composite. Maybe you can write it as m times n, as the product of two smaller things. Well, then you run into the same problem. That g to the m would end up being a proper subgroup as well, and so it wouldn't be simple. Same problem as before, really. So the only way that that's not going to happen is if it's a prime number, if the order is prime, because only then will there be no smaller thing which would be a proper subgroup, right? If it's a prime number, then anything you try to generate, you try to use to generate, will end up generating the entire set. Okay, so great. So that's in one direction, and now they went for the other direction. So suppose that the order of G is prime. Well, so then they do the same trick. They take a particular element, and we know that the order of it must be a divisor because it's a subgroup. But since it's prime, there's only one thing it can be, because there's only one divisor of a prime number, and that's the number itself, and also 1, of course. So it turns out that it's cyclic, and right, it's cyclic, and since it's of prime order, then there's no way to get a subgroup of it, because any subgroup would have to be of divisor order, and so the only subgroups are of order 1 and P, so there are no proper subgroups. In other words, it's simple, right? Now, of course, normally that's not equivalent to being simple, but for abelian groups, right, the normal thing is not important. So having no proper subgroups is the same as being simple. And so there you go. So both ways, the student just showed that being in, if you're an abelian simple group, then you are definitely isomorphic to ZP. Actually, I guess they didn't have to go both ways, did they? It only asks for one way. If simple, then... So I want to add on to what I recorded earlier on question 5. This student's submission for question 5, I was totally interpreting it wrong at the time I was recording. This is not an if and only if. This is if... Oh my goodness. Mistake. I gotta bring this back down. if you're a simple abelian group, then you're isomorphic to ZP for some prime. So this was not actually a bidirectional thing. This was only a one-directional thing. So this section here is actually sufficient for this problem. You don't need to go back the other way. Although it's interesting to note that you can go back the other way. Certainly ZP is a simple abelian group. So the second portion is totally legit, but unnecessary. You only need to do the first portion. So if simple, then it's prime. And this person concluded that, yeah, the order of G is prime. And if I remember correctly, in the last exam, you proved that if your order is prime, then you're isomorphic to ZP. So they adequately left that part off. So yeah, so only the first portion was necessary, not the second portion. This is only a one direction, not a two direction. But besides that, though, that's fine. This is a great solution.